Hey everybody, here's the last lesson of the semester. This is a catch-up that is a result of the switching around in chapters 7, 9, and 10 that we did to try to maintain alignment with the labs, where we skipped rotational kinetic energy. So I just want to explain this really quickly for you, and it should be pretty sensible and straightforward because as we've seen with everything with rotational energy, it's just like what we have, or with rotational motion and everything, it's like the linear version. There's just a one-to-one analog between rotational motion and linear motion. So we saw that with the equations, the kinematic equations for like rotational velocity and rotational acceleration correspond to the same form of equation for linear velocity and linear acceleration. And you remember that there was a version of Newton's second law for rotation. Torque equals I times alpha instead of force equals mass times acceleration. So torque is the rotational version of force, moment of inertia is the rotational version of mass, and rotational acceleration is the rotational version of linear acceleration. So it stands to reason that there would be a rotational kinetic energy. If something's rotating like this, there's motion there. There's obviously energy involved with that, even though it's not moving. There's no v, there's no velocity of the thing going across the room, but it does have energy. And so that rotational kinetic energy, I'll just call K rot, is equal to the same exact form that we have for linear kinetic energy, except instead of mass, we have the rotational version of inertia, which is the moment of inertia. And instead of v squared, we have the rotational velocity squared. So the kinetic energy due to rotation of an object is just 1/2 I omega squared. So let's do a simple example. I'm just going to make one up. Suppose we have a person on a bike and moving at 10 meters per second down the road, and the bike wheels have a radius of, I don't know, bike wheels radius about, let's say, 30, let's make it bigger, 40 centimeters, and a mass of, bike wheels aren't that massive, but we'll make these a little bit heavy just for fun. Make them like 3 kilograms each. And the mass of the bike is, let's say, is a total of 12 kilograms, and the mass of the person is 60 kilograms. What is the total kinetic energy of the person and the bike? Okay, so we know before we had to worry about rotational kinetic energy, we would have said that we've got a translational kinetic energy that's just 1/2 mv squared. And so in that case, let me put a little t here for translational. In that place, in that case, kt is 1/2 times the mass of the person plus the mass of the bike, m bike plus m person. They're both traveling together at a speed of 10 meters per second. So we can just put those numbers in. We get 1/2 of 72 times 10 squared, or kt is 36 times 100, or 3,600 joules. So that's the translational kinetic energy, but there's also rotational kinetic energy of the wheels, which is 1/2 I omega squared for each wheel. For a bicycle wheel, it's got spokes. I'm a terrible artist. All of the mass is out here at the edge. Is at distance r from the axis. This thing is rotating like that. And so that means that I for the wheel is just m wheel times r squared. That's the equation for moment of inertia. So for each wheel, we have k rot equals 1/2 times m wheel, times I wheel times r wheel, sorry, 1/2 I omega squared. It's 1/2 times I wheel times omega squared. And remember that the relationship between linear velocity and angular velocity is just v equals r omega, which means that omega is v over r. So that's 10 over 0.4, 10 meters per second divided by 0.4 meters. The radius of the wheels is 40 centimeters, which is 0.4 meters. And the moment of inertia is the mass of the wheel, which is mr squared, which is 3 times 0.4 squared. And so for each one of those wheels, we have 1/2 times, let's go ahead and calculate the value of the moment of inertia of each wheel. It's 3 times 0.4 times 0.4 is 0.48 kilograms meters squared. So it's 1/2 times 0.48 times omega squared. And omega, we said, was v over r, which is, I'm sorry, I'm going back and forth between capital R and little r, but that was 10 meters per second divided by 0.4 meters, which gives us, I believe, 25 radians per second. And so k rot for each wheel is 1/2 times 0.48 times 25 squared. 0.5 times 0.48 times 25 times 25 gives me 150 joules. So that's per wheel. So the rotational kinetic energy of the two wheels is 2 times 150, or 300 joules. So the total energy of the bike, the total kinetic energy of the bike, is the translational energy plus the rotational energy. The translational energy was 3,600 plus 300. So K total is 3,900 joules. So in this particular example, the rotational kinetic energy was a little bit less than 10% of the translational energy, but it is a component of the energy that needs to be calculated. But it's the same kind of calculation you would do with linear kinetic energy. You just, instead of using mass, use the moment of inertia. And instead of using linear velocity, you use the angular velocity. And that gives you the total number of joules involved with the rotation of the object. It could be a ball rolling along. It could be a wheel rolling, as we've done in this example. Could be a windmill, and then the moment of inertia is different. There's that factor in there that you have to look up, but you can just look up what is the moment of inertia for a particular type of object. If it's a windmill rotating, a blade rotating around a center point, or it could be rotating around the end like this. There's just a different factor in front of that mr squared for the moment of inertia, and you can look that up in a table in your book. So that's the last thing about rotational motion that we hadn't covered. We have then, just to sort of summarize, we have x, v, a corresponds to theta, omega, alpha, and the relationship between these is v equals omega times r, this equals alpha times r, this equals theta times r. So that's all straightforward. The kinematic equations, you just replace, take the linear kinematic equations with x, v, a, and t, and replace them with theta, omega, alpha, and t. We had F equals ma becomes torque equals I alpha. So there's an equivalence between mass and moment of inertia. And the moment of inertia is equal to some factor times mr squared, where this factor k depends on what the object is and where the rotation axis is for that object. We have linear momentum P equals m times v, and we have angular momentum L equals I times omega. Again, just replacing the mass with moment of inertia, the v with angular velocity. And now we have translational kinetic energy is 1/2 mv squared, and rotational kinetic energy is 1/2 I omega squared.